So, as already explained, a moon, unaffected by any third force, runs at its orbital velocity on the basic orbit, which is a circular one. The resulting centrifugal acceleration of the moon is always precisely balanced with the gravitational pull of the mother planet. In reality, the moon rarely travels at orbital velocity, but sometimes faster and sometimes slower around the Earth. If it's running faster than orbital velocity, the centrifugal force is greater than gravity and it will move outward. Conversely, he will move inward. If it runs slower than this. So the moon goes around the Earth. When it goes at the farthest point from the Earth its speed is slower than its orbital velocity, and at the point closest to the Earth it goes faster. This is how the moon moves there and back around the base circle as it orbits. But this phenomenon is quite strange. Because if the moon rings faster than orbital velocity, it will move outward. And as it moves outward, gravity decreases at unchanged speed, and its speed has become even faster than orbital velocity. Then he would have to keep moving outwards and never come back. But the question is, how can this phenomenon be explained? Albert Einstein could perhaps very proudly claim that it cannot be clarified without the theory of curved space. That claim, to put it mildly, is pure fantasy and has no place here. Here in real physics, all physical problems are always treated in a real and concrete way. To explain this phenomenon, we only need to calculate the orbital speed of the moon using the inertial equation. Then this problem will solve itself. This equation describes the orbital speed of a body driven by a central body. Their limit is this is called the target speed. From this we see, when the moon's initial speed is less than the target speed, its speed becomes faster and faster, and when the initial speed is faster than the target speed, it becomes slower and slower. It always reaches the target speed in the end. With this, it is not difficult to understand why the moon always moves there and back from the base circle. For example, if the moon is at point E, which is r0 away from Earth, the orbital velocity at that point is equal to when it goes around the Earth at this speed, its orbit is circular without disturbance. Suppose the moon is running at a speed ve1 delta v faster than the orbital speed. Consider the delta v equal to the orbital velocity difference between point E and P asterisk, which are delta r apart. With the speed ve the moon is moved outwards. When it reaches its maximum speed at point P, this is the driving acceleration, a, here is equal to that of the Earth's gravitational field g star. Hence, so the Vp is equal to the orbital velocity at that point. And the orbital velocity difference between points E and P is this means that the target speed Vp has decreased by twice delta V compared to the initial speed Ve. We call this effect the double orbital velocity difference effect. But why is this? We decompose the orbital motion into two parts, one tangential and one radial outward. The advance of the tangential speed delta v is slowed down by the braking function of the gravitational field, and in the radial direction the orbital velocity will decrease again by 1 delta v even because of the greater distance. This decrease is an increase in instantaneous speed relative to instantaneous orbital velocity. This increase is also slowed down. So it's a total of 2 times delta v. Conversely, if the Moon is initially traveling at point E at a speed 1 delta v less than the orbital velocity, and moving radially inward by a distance delta r, its speed will increase by twice the orbital velocity difference between that distance. We considered the initial velocity to be greater and less than the orbital velocity, respectively. But that is not a condition. As shown, for example, in Calculate Moon Orbit, the radial movement of the Moon is caused by the influence of the Sun. In this case, the effect is also the same. So it is generally valid, as long as a circulating body moves outwards, its tangential speed will decrease by twice the orbital velocity difference between the radial distance covered, or increase inwards. The two examples, the Moon's initial speed being greater and less than the orbital speed, corresponds to the Moon's movement from point 7 to 1 and point 3 to 5, respectively. The question now arises, when the Moon, moving from point 7 upwards just above point 1, or from point 3 downwards just below point 5, reaches point 4 or point 6, its speed is already somewhat smaller or greater than orbital velocity. This means that the Moon's centrifugal force is already smaller or larger than the Earth's gravity. Why does it not return at this point, but only at point 3 or point 7? There must then be some physical mechanism to make this maneuver possible. This mechanism is called simply the inertia. We will explain this in detail in the next video. Using the double orbital velocity difference effect, the Moon's orbital speed can be easily calculated as long as its distance from Earth is given. As explained, the speeds at point 1 and 5 are the same as follows. They are equal to the base velocity. The radius of the base circle is r0. When Moon runs from point 8 to point 1, or from point 1 to point 4, its speed will decrease by 2 times the orbital velocity difference between the track. In the same way, the equations for points 4 and 6 are: let's replace the two radius from the four formulas by real radius r. The speeds at these 4 points are as follows. Then the orbital speed of the Moon of radius r can be expressed with just a single equation. It doesn't matter which direction it's running. So the orbital speed of the Moon, whose distance from the Earth is r, is twice the orbital velocity minus the ground velocity. Thank you very much for your attention. See you next time.